In this video, we solve problem 11.4.023 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to verify that the points are the vertices of a parallelogram and find the parallelogram's area. So I don't actually know which points are which. I don't know if this is A and that's B and that's C and that's D, or exactly how this is arranged, but I think one of the easiest things to do, or one of the easiest ways to start this, is to compute vectors from point to point. So let's say that A is at one location and B is at another location. We've got these coordinates and these coordinates. If we want the vector from A to B, we just take the coordinates of B, that's 2, 5, and 9, and we subtract the coordinates of A. So that's 1, 1, and 3. When we do that, we get 1, 4, and 6 as our components of the vector AB. Let's see if there's another vector that has the same components. How about we look at the vector from C to D? So the vector from C to D, in order to find the components of that vector, we take the coordinates of D, and then we subtract the components of C, coordinates of C. We have coordinates for points and components for vectors. And let's see what we get. We get -1, -4, -6. Now, those two vectors are parallel to each other. They're just running in opposite directions. So for my little cartoon over here, if this is AB, and I just came up with the vector from A to B, and this was the vector with components 1, 4, and 6, well, this is telling me that the vector that starts at C and goes to D is parallel, it just runs in the opposite direction. So I would say that this must be C and this must be D. Say, okay, well then let's look at the vector from B to C and the vector from A to D and see if those are parallel as well. So we'll compute the vector from B to C, take the coordinates of C, 4, 8, and 2, and subtract the coordinates of B, that's 2, 5, and 9. And of course, this is just a cartoon. I don't actually know what it looks like, but I'm just trying to prove that I've got parallel vectors here to prove that these are the vertices of a parallelogram. So we've got a vector with components 2, 3, and -7. Okay, so let's say that that goes this way. Let's look at the vector from A to D now. Take the coordinates of D and subtract the coordinates of A. So we get 2, 3, and -7. Great, so those are parallel to each other, and they're actually exactly the same vector. So if these are parallel and these are parallel, we do have a parallelogram. Now we want to find the area of this parallelogram. Well, the area of a parallelogram with U and V as sides, so let's say this is the vector U and this is the vector V, turns out to be equal to the magnitude of the cross product between U and V. So in our case, we need to find the cross product of the vector AD and the vector AB. And then once we find that cross product, we want to find its length. It turns out the length of that cross product vector is equal to the area of this parallelogram. So the components of AD go here. So it's 2, 3, and -7. The components of AB go here. Those are 1, 4, and 6. So we cross out this row and this column. Then we do this times this, so it's 18. And then we multiply across this diagonal. That's going to be -28. And then we subtract. So we have 18 minus a -28. So that's the same as adding 28 times I hat plus -1 times whatever we get when we cross out this row and this column. And then we have another determinant. So we're going to have 12 minus a -7. So that's 12 plus 7 there. And then for the last one, we'll have cross out this row and this column. We're going to have 8 minus 3, which is 5 times k hat. So that ends up being, what, 46 and -19 and 5. as the components of the cross product. That's a vector that's perpendicular to both of these guys. It's going to point straight up out of the page if these were actually our vectors A, B, and AD. But we don't actually want that vector. We want the magnitude of that vector to find the area of this parallelogram. So that requires taking these components, squaring them, and adding them, and taking the square root. So our components were 46, negative 19, and 5. So that's our area. And I'll just use a calculator for the arithmetic. 46 squared plus 19 squared plus 5 squared. Square root of the answer is equal to 3 times the square root of 278. And that's my exact answer. WebAssign probably wants the exact answer, but let's see what it is if we want a decimal approximation. That's approximately 50.019996. I'm not sure how many decimals they would want us to round to. We'd have to look at the fine print in WebAssign to see if they want this, or if they want this, or if they want some rounded version of this.